All right, welcome everybody at this webinar of the webinar series on BD-RIS, the second edition. Today is my great pleasure to introduce you our speaker, Liang Liu, professor at the Hong Kong University, Hong Kong Polytechnic University. So let me briefly introduce his background because before giving him the floor, Liang Liu is currently associate professor at the Department of Electrical Electronic Engineering at the Hong Kong Polytechnic University, and he's an IEEE ComSoc distinguished lecturer for this year. He's a recipient of the 2021 IEEE Signal Processing Society Best Paper Award and the 2017 IEEE Signal Processing Society Young Author Best Paper Award, and the Best Student Paper Award for the 2022 IEEE International Conference on Acoustic Speech and Signal Processing, and the Best Paper Award also in 2011 at the International Conference of Wireless Communications and Signal Processing. He's also editor for several journals such as TWC and TSP. So very nice to have you, Liang, today. And let me remind you a few rules for the audience. The talk is expected to last approximately 50 minutes, after which there will be a Q&A sessions. The audience will be muted during the talk, but feel free to type your questions in the chat or maybe raise your hand at the end. And enjoy the talk. And Liang, the floor is yours.
Okay, thank you for introducing me. So I will share my slides. Can I see it?
Yes.
Okay, great. Okay, hello everyone. Today I'm very honored to give a talk about BD-RIS at this webinar. I'm going to talk about the channel estimation issue in BD-RIS. And basically, I want to show that the overhead for BD-RIS aided communication for the channel estimation issue, this overhead is similar to that in the conventional RIS aided communication. So you don't need to worry about the channel estimation issue in BD-RIS aided communication. First of all, I briefly introduce the RIS, which is already well known, right? So RIS is a very hot topic. I think all of you are very familiar with this. And for the RIS, the basic idea is to change the channel such that it is good for communication. And for each RIS, we have several reflecting elements. For each element, for the conventional RIS, we also call this diagonal RIS. All the elements are not interconnected. This means that if there is some signal received by the first element, then this signal will only be reflected by the same element. We only change the phase. And the signal will not be propagated to the other reflecting elements. Mathematically speaking, this means that for the scattering matrix phi, this should be a diagonal matrix. If we have m reflecting elements, then this is a m by m diagonal matrix. And phi m is the phase, the reflecting coefficient corresponding to the m's reflecting elements. And you only change the phase, so the amplitude of each coefficient is 1. And from the optimization perspective, you may ask, can we have more freedom to design the reflecting matrix? And this gives rise to the new type of RIS. We call it BD-RIS. I think Bruno and Matthew, they are playing a very pioneer work in this area. So the basic idea is that now all the reflecting elements are interconnected. If you, for example, for the first reflecting element, it will receive some signal, but this signal will be also propagated to the other reflecting elements, and all the other elements will change the propagation property of this signal received by the first element. So mathematically speaking, this scattering matrix phi will be a non-diagonal matrix, and we have many non-zero offset of diagonal elements here. But to make the power satisfy to satisfy that the output power is equal to the input power, we have this unitary matrix constraint on the scattering matrix. there are some prototypes to make this BD-RIS. For example, Bruno or Rosmers, they have designed different prototypes for BD-RIS separately. So if we just look at the rate optimization problem, then we are very happy because for any diagonal matrix phi of the conventional diagonal race, it is a special case of the new BD-RIS scattering matrix phi because for any diagonal matrix, it is a unitary matrix. And this means that if we do the optimization, we have more freedom to design a new non-diagonal matrix phi. We can achieve better rate. From rate perspective, this is good, but the question is that does this mean if in the future we use BD-RIS in the practical system, the network throughput is definitely better than that achieved by the conventional diagonal RIS? The answer is not yes, or we cannot say definitely yes. We need to think about it. The reason is that in practice, before we transmit the data, we need to estimate the channel. After we know the channel, we can design the beamforming vectors at the race and at the base station set. But if we just look at data transmission rate, maybe BD-RIS gives better performance, right? But the issue is that if we consider the channel estimation overhead, maybe we need to estimate far more channel coefficients in BD-RIS aided communication. Then maybe we use quite a lot of time to estimate channel. We don't have sufficient time to do data transmission. So overall, the number of bits transmitted in each coherence block maybe is fewer than that in the conventional RIS-aided communication if we consider channel estimation overhead, right? We have a lot of examples. For example, for massive MIMO, the beamforming gain is higher. But for downlink massive MIMO in FDD system, we have to estimate the channels in the downlink. Then the overall throughput is not as good as the conventional MIMO system because of this channel estimation overhead issue. So in practice, if we consider channel estimation overhead, currently we cannot say definitely BD-RIS aided communication is better than the conventional RIS aided communication. So in this talk, we want to show the channel estimation issue is not a big one for BD-RIS aided communication. But before that, I want to emphasize channel estimation can be a very important issue. And the example is like this. Now let's consider conventional RIS-aided communication. This is a diagonal RIS. We have one single antenna user, and this is a RIS with M reflecting elements. There is one base station with N antennas. And in this case, let's use Rm to denote the channel from the user to the M's reflecting elements of the RIS. So we have this vector R, which consists of R1, R2 until Rm. This is M by 1 vector from the user. This is the channel from the user to the RIS. And for reflecting element M of the RIS, its channel to the base station is denoted by GM. This is N by 1 vector because we have N antennas at the base station set. And again, we can design a big matrix G. G consists of G1 until GM. So this is the overall channel from the RIS to the base station. This is N by 1 matrix. And this is the setup we are considering for the conventional RIS-aided communication. So in this case, if we transmit a pilot signal AT at time slot T, this is the received signal of the base station. Let's assume we don't have this direct channel, we just have this reflected channel from the RIS. So P is the transmit power. Phi MT is kind of the reflecting coefficient of the M's elements at time slot T. And HM is the cascaded channel from the user to elements M of the RIS to the base station. It is the product of Rm and the GM. This GM is a vector. So this is the contribution made by reflecting element M. And we have M reflected elements, so we add them together. This is the received signal at base station at time slot T. And this is well known. I don't need to explain this in details, but the thing is that we need to estimate M cascaded channels, H1 until H capital M, these M cascaded channels. And each cascaded channel is n by 1 vector. We have n antennas at the base station. We have m this kind of vectors. So overall, we need to estimate mn unknowns. Let's assume we don't have this noise, okay? Just we have these linear equations. And we have mn unknowns in these linear systems. How many equations do we have? For each observation, we have n right, this n by 1 vector, we have unknowns, right? And suppose we have t time slots to estimate the channels. We have n times t equations, linear equations. So to make a unique solution in this linear system, we need to guarantee the number of unknowns is equal to the number of equations, right? So in this case, t should be equal to m to guarantee we can estimate these cascaded channels. Now let's look at the BD-RIS system. And now for the BD-RIS, the difference is that now suppose the user transmits some parallel signal in uplink. This is the received signal as reflecting element M. But now, because this is a BD-RIS, all the elements are connected by some circuits. This means that this received signal can be propagated to this element, propagated to this element. It can be propagated to all the elements. So this signal will be reflected by all the elements to the base station, not just elements n. So if we look at the received signal, okay, let's say this phi t is the scattering matrix at time slot t of this BD-RIS. And this is the amps columns. Phi tm is the amps column of this scattering matrix. And this is the contribution of the signal received by element m and reflected by all the elements here. And this phi m is the cascade channel. But because this signal will be propagated to all the elements, so this cascaded channel now is the product of Rm and G. G is the collection of all these channels from each element to the base station. Okay, because all the elements will reflect this signal received by elements M. So now we can see that now the cascade channel, the dimension is higher. This is QM, the product of Rm and G. And this is the received signal contributed by the signal received by element M. And we add all the M elements together. This is the received signal at the base station set. And we need to estimate this QM for channel estimation. So now the difference we can see is that we also need to, for example, estimate Rm times, for example, this is Gm minus 1, because this signal will be propagated to elements m minus 1 and reflected to the base station. We also need to estimate this kind of channels in BD-aided communication. Previously, for conventional RIS, diagonal RIS, we just need to estimate PM times GM, right? Now we need to estimate many, many more channel coefficients here. And again, let's assume there's no noise. Let's see how many time slots do we need to estimate these channels. And now recall that we need to estimate QM. M starts from 1 to capital M. And each QM is a n by m matrix because we have m elements and the RIS n antennas at the base station. And we have m, this kind of matrix. So overall, we have n times m squared unknowns in Q1 to Q capital M. Okay, so the number of unknowns is increased significantly. And the number of linear equations is what each yt is n by 1 vector, right? N knowns, n observations. We have t time slots. So overall, we have nt linear equations. So if we just look at this as a linear system, we need to guarantee the number of unknowns is equal to the number of equations, right? And then we need to make t is equal to m squared, right? We need this number of time slots to estimate all the m cascaded channels. So remember, for the conventional diagonal RIS, the number of time slots required to estimate the channels is m. But now it is increased to m squared. The order is increased, right? So this means that, okay, if this is true, right, we need to use much more time to estimate channels. And then the issue is that although the beamforming gain is higher in the data transmission phase, but we use too much time to estimate channel. Maybe overall the throughput is not as good as conventional RIS-aided communication. It's very possible, right? So the issue is that is this the best we can do? And in this talk, the key conclusion is that, okay, we can show the overhead for channel estimation in BD-RIS aided communication and conventional diagonal RIS aided communication. These two overheads are of the same order. Okay, we don't need to worry about the channel estimation issue. This is the conclusion. Suppose we have one RIS consisting of M elements. We have a base station of N antennas, and we have K users. Each user has U antennas. So this is a very general BD-RIS or RIS-aided MIMO communication, multi-user MIMO communication. And let's say Q is the rank of G. G is the channel from RIS to the base station. And we can show that the overhead for channel estimation in BD-RIS aided communication is this 2M plus some term. But the issue is that it is linear in M, not M squared. Okay. And I want to introduce another of our previous work. In this work, okay, in reference 6, we saw that in the conventional diagonal RIS-aided communication, this is the overhead for channel estimation issue in the same setup. Just the BD-RIS is changed to the conventional diagonal RIS. It's still linear to M, okay? And this is a ESI hot paper. The citation is 900, more than 900 on Google Scholar now. If we compare BD-RIS and conventional RIS, we can see that they are almost the same in terms of the channel estimation overhead. Just this M is increased to 2M, but the order is the same. This is good news. So in the rest of this talk, I want to show this result, okay? But this means that the channel estimation overhead is of the same order. And for beamform design, BD-RIS is better. So we can say that, yes, if in the future we use BD-RIS in practice, the network throughput can be better than the conventional RIS-aided communication. This is our conclusion. So before I introduce the BD-RIS channel estimation, I want to briefly introduce our previous work for conventional RIS channel estimation in conventional RIS-aided communication. Because for BD-RIS, a lot of things are similar. This is beneficial, okay? So let's start with the case when we have multiple users, multi-antenna user. And this RIS is a diagonal RIS, not BD-RIS. Later we will show the BD-RIS case, okay? And so we just need to estimate the cascaded channel kind of HKM. This is the kind of RKM times GM, okay? We just estimate this kind of cascaded channels in diagonal RIS-aided communication. And this is the receive signal. We need to estimate HKM. M can range from 1 to capital K. K is the number of users. And M starts from 1 to capital M. M is the number of RIS elements. And we have shown that in this case, we need to estimate, we need to guarantee T is equal to MK if we view this as a linear system, right? We have NT equations, and the number of unknowns is KMN. Now we have K users, okay? So overall, there are KMN unknowns in all these cascaded channels. So we need to guarantee T is equal to MK such that the number of equations is equal to the number of unknowns. But this is not the best we can do. What is missing here? So let's look at reflecting element M. If we look at user 1, this H1M is equal to R1M times GM. If we look at capital K, this user K, HKM is equal to RKM times GM. This GM is common in all these cascade channel because this GM is shared by this channel and by this channel. So although they are two vectors, but actually their directions is the same, just this scalar coefficient is different in these two vectors. So they have strong correlation. And we can mathematically model this. For example, H1M is the product of R1M and GM. HKM is equal to RKM times GM for each K no smaller than 2. And this means that for K larger than or equal to 2, I can express its channel HKM as the product of bit Km and H1M. Bit Km is the ratio between RKM and R1M, okay? And this means that if we know H1M, when we estimate HKM, K is larger than or equal to 2, then we don't need to estimate the whole vector. We just need to estimate one scalar bit Km. After we know bit Km, we multiply it by H1M, we know the overall vector here, right? This is n by 1 vector. But to estimate H2M, for example, I just need to know bit 2M. I don't need to know the whole n unknowns here because I already know H1M. So this means that previously, if we estimate H1M, H2M until H capital Km, right? Now what I want to do is that I want to estimate H1M. This is the reference vector. But for K, starting from 2 to capital K, I just need to estimate bit 2M, bit 3M until bit Km. Because after I know these scalars, I multiply them by H1M. I know the overall channel, okay? So here, from H1M to HKM, I have KMN unknowns. But if I use this beta M, right, I estimate these channels for H1M. This is n by 1 vector. I have M this kind of vectors. So I have Mn unknowns for H1, H12 until H1 capital M. And for beta, right, K starts from 2 to capital K. M starts from 1 to capital M. So I have K minus 1 times M unknowns in beta. So this is the overall unknown if I do this transformation. This is much smaller than KMN, right? So this is the trick we are playing. And now I want to replace HKM by bit Km times H1M, right? So this is the reflected signal contributed by the first user. And this is the signal from the other K minus 1 users. So I replace HKM by bit Km, right, times H1M. This is the trick I'm playing. The good news is that now the number of unknowns is smaller. But the bad news is that now this is not a linear equation, even if we ignore the noise, right? This is linear in H1M, but I don't know beta, I don't know H. We have the product of beta and H. So how to solve nonlinear equations? For the linear system, we know that if the number of equations is equal to the number of unknowns, we can uniquely solve this linear system, right? But for the nonlinear system, we don't have such results. We don't know how many equations are needed to estimate these unknowns here. So this is the challenge that we need to tackle. So our approach to deal with this nonlinear issue is to do sequential estimation. So we divide the whole time slots into two phases. In phase 1, we just let user 1 to transmit the pilot signal, A1T, okay? And the other users will not transmit any pilot signals. So the received signal will only contributed by this term. This is linear in H1M, right? We can take some time slots to estimate H1M. M starts from 1 to capital M. And in phase 2, the other users can transmit, but I already know H1M, right? And if I know H1M, then YT is a linear function of beta, right? So in phase 2, the other users can transmit, but I know H1M, I can solve these linear equations, and I know what is beta, right? So this is our sequential estimation approach. And we can show that if we just have one antenna at each user, this is the number of time slots to estimate H1M and bit Km, this kind of unknowns. And if we have U antenna users, this is the number of time slots for channel estimation. So this is the main result of our paper, and we are the first to review this hidden property in the different users' channels. We saw they are correlated. We can use this property to reduce the channel estimation overhead. So this is our contribution. So now let's move to the topic of this talk, BD-RIS, right? And now for the BD-RIS edit system, how many time slots do we need to estimate the channels? And let's start with the case that we have one single antenna user. Later, I will briefly extend the results to the case with multiple multi-antenna users, okay? Let's start with the easiest, simple, one user, and it has one single antenna. And there is one BD-RIS consisting of M elements, and there is a base station with of N antenna. There is a base station of N antennas. This is the system we are considering. And this is the received signal. Remember, this is the signal contributed by the signal received by element M, and it is reflected by all the elements to the base station because the signal can be propagated to the other elements via this interconnected circuits. And we add all these M terms together. This is the received signal at time slot T. And we want to estimate Q1 until Q capital M. And each QM is a cascaded channel. Its dimension is n by m, right? And if we don't do anything, at the beginning, we have shown that we need m squared times loss to estimate Q1 until Q capital M. This is not linear in M. If we have diagonal rays, the number of times loss is linear to M, right? Can we reduce this channel estimation order in the BD-RIS aided communication? This is what we are trying to answer in this talk. Again, if we look at Q1, Q2 until Q capital M, you will find, okay, again, some common term appears in all of this cascaded matrix. Okay, this is G. G is the channel. G is here, the channel from the RIS to the base station. This is the overall channel from the RIS to the base station, right? This is because for the signal received by element M, it is reflected to the base station via this G. For the signal received by another element, maybe M minus 1, this signal will also be reflected to the base station via this overall channel G. So this G, this channel is common in Q1, Q2 until Q capital M, right? And this means that, again, Q1, Q2, and QM, these cascaded channels are very correlated. They are not independent. The key idea is that if you have independent unknowns, right, you need to guarantee in the linear systems, the number of equations should be at least equal to the number of unknowns. You can solve these linear equations to do channel estimation. But now in this system, Q1 until Q capital M, they are correlated. If they are correlated, we have the opportunity to reduce the number of equations to solve to estimate these unknowns. This is the trick we are playing. And similarly, okay, if you still remember the diagonal risk case, okay, here everything is quite similar. And for Q1, okay, it is the product of R1 and G, right? R is the channel, the scalar channel from the user to one element of the race. G is the overall matrix, channel matrix from the race to the base station, right? Q1 is the product of R1 and G. And for the other M starts from 2, okay? QM is equal to the product of Rm and G. G appears in all these Q matrices. And we can also play the trick. For any M no smaller than 2, we can express QM as the product of BM and Q1. Okay, this is the relation between QM and Q1. Here, beta M is the ratio between Rm and R1, right? So again, this means that if we can estimate Q1, after we know Q1, we don't need to estimate Q2, all the elements in Q2, all the elements in Q3, all the elements in Q capital M, right? We just need to know beta 2. After I know this scalar beta 2, I multiply it by Q1. Then I know everything about Q2, right? And after I know beta 3, I can know everything about Q3. So again, the number of unknowns is not as large as what we have expected. So previously, in the conventional approach, the overhead is m squared. This is because we treat all the elements in Q1, Q2 until Qm independently, right? But now, if we do the replacement, we just need to estimate Q1, and for the other elements, we just need to estimate beta 2, beta 3 until beta capital M, right? And in Q1, Q2, Qm, we have n times m squared unknowns. But if we do this replacement, we just need to estimate Q1 and n unknowns in Q1, right? And then we need to estimate beta 2, beta 3 until beta capital M minus 1. There are M minus 1, this kind of scalars. So now the number of unknowns is reduced to Mn plus M minus 1. This is much smaller than what we believe, right? Previously we say it's nm squared. now it's linear to M, right? Now you can intuitively believe my result is correct. My result is that the channel estimates overhead in BD-RIS aided communication is linear to M, not M squared. The order is M, not M squared, right? So this is the similarity. That's why I introduced the conventional diagonal RIS first. So if we have multiple users and for any two users, right, they share the same channel from element M to the base station. Just this scalar part, right, is different. So these cascaded channels are correlated. We can use this property to reduce the channel estimation overhead. And for BD-RIS, if we just have one user, it's the same. We have, for example, this is the channel to element M, and this is the overall channel G. Maybe another signal is to element M minus 1, but again, the signal will be reflected to the baseline by this common G, right? This G is common. And based on this property, we can reduce the channel estimation overhead in BD-RIS aided communication. So actually, mathematically, we are playing a very similar trick in both of these two works. Anyway, now I want to show how to do channel estimation in BD-RIS aided communication. And this is the receive signal, okay? And again, I want to replace Q2, Q3 until Qn-1 by the product of beta m and Q1, okay? I want to relate Qm to Q1. I want to reduce the number of unknowns in these equations. This can reduce the number of unknowns, but the problem again is that this is not a linear equation, right? We have the product of beta m and Q1. Both beta and Q are unknowns here. Both beta m and Q1 are unknowns here. And how to deal with this nonlinear issue in these equations, right? And another challenge is that we have the unitary matrix constraint. This is the limitation caused by this circuit. We need to guarantee the output power is equal to the input power. So why this unitary matrix constraint is a big challenge? So at the very beginning, we think about this approach. We also want to do a sequential estimation. Remember, for diagonal RIS, we do sequential estimation, right? The issue is that can we, for example, in the first phase, we shut down the other elements. We just turn on the first elements. So we hope that phi tm is equal to 0 when m is equal to 2, 3 until capital M minus 1. At the beginning, we hope this term is 0. So the received signal is only contributed by this term. This is linear to Q1. We can estimate Q1. And in the second phase, we turn on all the elements. Then we already know Q1, then this is a linear function of beta m. Then we can estimate beta m, right? By solving some linear equations. But the issue is that if we have a unitary matrix constraint, this is not feasible. Because in phase 1, we just want to turn on the first elements. The other elements, the reflecting elements, reflecting coefficients are 0. So the first column is non-zero, the other elements, the other columns are 0. This is not a unitary matrix because a unitary matrix must be a full rank matrix, right? This matrix, the rank is 1. It cannot be a unitary matrix. So physically speaking, the reason is that now you hope that a signal is received, for example, by the first element, and it can be reflected by the other elements. But you hope for the signal received by, for example, element 2, it cannot be reflected by the other elements. This is not possible, right? If you want to use element 2 to reflect the signal received by element 1, it means that element 2 is already on. Then it can receive the elements, and this signal should be reflected. So if phi t1 is non-zero, it means that phi t2 cannot be non-zero. So due to this interconnected elements, interconnected circuits, you cannot use this sequential estimation approach to separate the estimation of Q1 and beta m. We have to estimate them jointly. So what we are doing is quite interesting. So we can show that we can use 2m time slots to estimate the channels. The basic idea is still like the basic principle is that we still want to cancel this term, right? Because this is the nonlinear term. We still want to cancel this term. We estimate Q1 first, and after we know Q1, we use this to estimate beta. Still, we want to use this approach, but we cannot use sequential estimation approach to achieve this goal. So what we do is that we divide the overall 2m time slots into 2 blocks. Each block consists of m time slots, okay? So the first block, it consists of time slots 1, 2 until capital M. And the second block, it consists of time slots m+1, m+2 until time slots 2m. So let's look at block 1. In block 1, the user can transmit an arbitrary pilot signal at time slot t. We just need to guarantee the power is 1, okay? And let's look at how we design the RIS scattering matrix. So the basic idea is that in time slot 1, we can generate an arbitrary unitary matrix. Let's say the first column is P1, the second column is P2, and the last column is P capital M. And in the second time slot, we just shift all the columns to the left by 1 position. Okay, P2 will become the first column, P3 will become the second column, and the PM will become the M-1 column, and the P1 will move to the right, become the last column. Okay, we shift everything to the left by 1 position. This is how we get phi 2. And for phi 3, okay, we shift all the columns of phi 2 to the left by 1 position. We keep doing this. And at time slot capital M, phi M is this. The first column is PM, and then P1, P2 until PM-1. We generate the scattering matrix like this. Why we do this? We can prove that if phi 1 is a unitary matrix, if we do this shift, okay, we can guarantee phi 2, phi 3 until phi M, all of these matrices are unitary matrix. We need to guarantee the scattering matrix is a unitary matrix at each time slot. And this property can be achieved if we do this kind of circulant shift. And then let's look at block 2. Okay, block 2 consists of time slots m+1, m+2 until 2m. And the basic idea is that we pair 2 time slots together in block 1 and block 2. For example, time slot 1 in block 1 and time slot m+1 in block 2. These 2 time slots will be paired together. And time slot 2 and time slot m+2 will be paired together. And at last, time slot m and time slot 2m will be paired together. Then we have m pairs. And for each pair, we guarantee their pilot signals are the same. For example, for time slot m+1 and time slot 1, their pilot signals should be the same. And also a m+2 is equal to a2. A m+3 is equal to a3. Okay, for each pair, if we look at these 2 time slots, the transmitted pilot signals should be the same. And then for the RIS scattering matrix, what we do. And again, each pair consists of 2 time slots, okay? And for these 2 time slots, we need to guarantee for the phi matrix, the last m-1 columns are the same. Their difference is in the first columns. The first column is changed. Now I give you one example. For example, for phi 1, okay, I already gave you this P1, P2 until PM. And for phi m+1, okay, remember time slot 1 and time slot m-1, these 2 time slots are a pair. And then if we look at phi 1 and phi m+1, you can see that everything is the same, P2, P3 until PM, but the first column is different. For m+1, the first column is e to the power of j theta times P1, okay? So there is a new coefficient here. Previously, we just have P1 in phi 1, okay? Now we just change the first column. We multiply it by a coefficient e to the power of j theta. The other columns, everything is the same as phi 1, okay? Phi 2 is generated by, phi m+2 is generated by, based on phi 2. And phi 2m is generated by, based on phi m. So all the other columns are the same, right? Here is the same. Just the first column previously is PM. Now I change it to e to the power of j theta times PM. So first of all, I can still show if I generate phi m plus 1, phi m plus 2 until phi 2m as this, then they are again the unitary matrix. They satisfy the unitary matrix constraint. And now let's look at the receive signal if we design the payload and the scattering matrix like this. This is the receive signal in the first block. This is the receive signal at the second block. Okay. Remember, we pair two time slots together. Time slot t in the first time slot and time slot m plus t in the second block will be paired together. And if we look at yt, this is the signal received at time slot t, and ym plus t, this is the signal received at time slot m plus t. Okay, we will find, okay, because we use this approach, the payloads are the same, and for the scattering matrix, the last m plus 1 columns are the same, only the first column is different. So if we have this property, we can guarantee for yt and ym plus t, these two time slots in one pair. The received signal contributed by the other m minus 1 reflecting elements are the same. This term is the same because we guarantee the same plots are transmitted, the same scattering columns are used. Only the signal contributed by the first reflecting elements of the RIS will be different because I changed the reflecting coefficient in the first row a little bit, right? We have e to the power of j theta here. So this part is different. But the second term, this is contributed by the other m minus 1 reflecting elements of the RIS. This term is the same. The first term contributed by the first reflecting elements, this is the same. And if I have this property, what I can do is that I take the difference between y and plus t and yt. This is one pair of the received signal, right? For time slot t in time slot in block 1 and time slot m plus t in block 2, I pair them together. And if I take the difference between ym plus t and yt, then I can remove this part, right? This part is the same in yt and ym plus t. So I can remove this part by taking the difference between ym plus t and yt. I just have the signal contributed by the first reflecting elements, right? E to the power of j theta minus 1 times q1 phi t1, and this is the payload signal. So for each pair, I have a linear observation of q1, right? I have m pairs, then I have m this kind of linear equations. But I can accumulate them together. Then I can say that delta y1 until delta y capital M, it is kind of this. You combine them together. This is the overall linear equations. And now we have how many unknowns here? M times n unknowns in Q1, right? This is a m by m matrix. Then how many observations, how many equations do we have? Each delta y is an n by 1 vector, right? We have m this kind of equations. So we have n times m linear equations. We have n times m unknowns here, right? The only thing we need to do is that we need to guarantee this matrix is a full rank matrix. If this is a full rank matrix, then we can guarantee we can uniquely solve these linear equations to estimate Q1, right? So we can prove, okay, this is a full rank matrix. Why? Actually, it's quite simple. Remember, P1, P2 until Pm, this is a unitary matrix. It's a full rank matrix, right? Now I just multiply some scatter, some scalar coefficient A1 onto Kam. A is the payload transmitted at this time slot, right? And you multiply each column by a scalar, it will now change the rank of this matrix. So this is still a full rank matrix. The rank is M. And if we can prove this is full rank matrix, then we have Mn linear equations, we have Mn unknowns, then we can uniquely solve these linear equations. We can estimate Q1 uniquely based on this linear system. So that's why we can use 2m time slots to estimate Q1. Okay, This is the first result. So now after we know Q1, we remove the first term from YT. Okay, remember this is YT. After I can estimate Q1, I can remove this term. Okay, and then I just have this signal contributed by the other n-1 reflecting elements, right? Here we have beta m. We want to estimate beta m, and Q1 is already known, right? If it is not known, this is the product. This is nonlinear function of beta m and Q1. But the good news is that now we already know Q1. And after we know Q1, this is a linear function of beta m, right? And actually, we can write down this as a linear matrix form. Again, we can show this FT is a full rank matrix, and by using these equations, we can uniquely estimate beta 2 until beta m. So this completes everything. With 2m time slots, I can first estimate Q1 based on this approach, right? And then I can estimate beta m based on these equations. So if you give me 2m time slots, I can estimate Q1 and beta m, all these unknowns. So this is the case when we have one single antenna user. And you may ask, what if we consider the general case? We have k users, each user has u antennas. This is a multi-user MIMO case. This is very general, right? I don't have too much time to explain it, but I can show the basic idea. The basic idea is that in this case, you have KU transmit antennas, right? And the signal will be contributed by all these KU transmit antennas. So what we can do is that we divided the overall time slots into two phases. In phase one, you can only turn on the first antenna of user one, okay? And you turn off all the other antennas. Then the received signal will be only contributed by antenna one of user one. And this is the scenario with one single antenna user, right? We have already saw how to estimate this Q11. And then when Q is known, you can turn on all the other antennas. But after you know Q, your job is to estimate beta, right? After you know beta, you know how to estimate the other cascaded channels, right? So the idea is similar. We just turn on antenna one of user one in the first phase, and we use what we have introduced at the beginning to estimate Q11. Okay, after we know Q11, the job is to estimate beta. You can turn on all the other antennas. And this is a linear function of beta. You can solve linear equations. But it's quite challenging if you look at our paper, because eventually you need to show, okay, a matrix is of full rank. And then the proof can be quite challenging, but we are able to prove this. So that's the basic idea. After we know Q111, we can show how many time slots are needed to estimate beta for all the antennas, all the other antennas. So due to the time limitation, I think I will skip these results. But the thing is that based on our approach, we can show, okay, if we have k users, each user has u antennas, and we have arrays consisting of m elements, we have one base station with n receive antennas. Then in the uplink, this is the channel estimation overhead, okay? And remember, for the conventional diagonal RIS, this is the channel estimation overhead. The second term is the same. The first term, it is increased from m to 2m. It's larger, right? But the good news is that the order is the same. It's linear in m. This means that if we just look at the overhead to estimate channels in BD-RIS aided communication and in conventional diagonal RIS aided communication, their orders are the same, right? And if the channel estimation overhead is similar and we have higher beamforming gain in the BD-RIS aided communication, so overall the throughput can be anticipated to be larger, right? And this gives the conclusion that in the future it's very promising to use BD-RIS to improve the network throughput. And this is one simulation result. X-axis is the pilot sequence length. Y-axis is the normalized MSE for channel estimation. And we can see that for our approach, the channel estimation MSE, normalized MSE, is very small when the number of times parallel sequence length, when the parallel sequence length is small. This is because our scheme requires a very small overhead for channel estimation. For the other benchmark schemes, they require very long parallel sequence to estimate all the channels. So when you have fewer time slots to estimate channels, our approach can achieve the best performance. The channel estimation MSE is orders of magnitude smaller than the benchmark schemes. This is very promising. So at last, I think I can conclude this time. I think the time is perfect, right? 50 minutes. So in this talk, we have characterized the channel estimation overhead in BD-RIS aided communication. And the good news is that it is in the same order of the channel estimation overhead in conventional diagonal RIS aided communication. So this means that you don't need to worry about the channel estimation issue, right? You shouldn't worry about the channel estimation overhead. But if we want to estimate channel, actually the algorithm to estimate channel is more challenging than that used for conventional RIS. But anyway, we can use more advanced signal processing technique to estimate channel with the similar overhead, right? The channel overhead orders are similar in BD-RIS aided communication and the conventional diagonal RIS aided communication. This is the best news we have shown in this talk. And people have shown for beamforming design, BD-RIS has more freedom, right? We can achieve higher beamforming gain. Then overall, you can achieve this beamforming gain for free, right? Because you use similar overhead to estimate channel compared to the conventional RIS aided communication. So BD-RIS is a very promising technique in the future. So I think that's all. Thank you very much.
Thank you so much, Liang. Thank you so much. Very, very clever idea and very clear. We have a question. Please, Yang, feel free to unmute yourself and ask. Hello, can you hear me?
Yeah, I think you can unmute yourself. I cannot hear you.
Hello, you cannot hear me?
You can unmute Yang, I think. He cannot open the
Uh,
microphone. Maybe you can
uh,
type your
yeah,
question
feel free
here.
to type your question.
Have
Okay.
you considered group connected architecture? Yes, I have. We have just submitted a letter to consider group connected architecture. We have good news and bad news. The good news is that uh, this kind of property I show you, this kind of property can still be used for group connected BD-RIS. We can still use this property to reduce the channel estimation overhead. We can propose some algorithm. Oh, I forgot to mention something. So in this talk, I mainly focus on the case when we don't have noise because I want to show, fundamentally speaking, how many time slots are needed to perfectly estimate these channels. So we need to ignore the noise. But in the paper, we also consider the case when we have noise. And when we have noise, we can still first estimate Q1 and then estimate beta. We can still do this, but maybe we use MMSE or linear MMSE estimators. And for group connected BD-RIS, the good news is that when we have noise, we can still use this property to estimate Q and beta separately. We can design maybe MMSE or linear MMSE estimators. But the bad news is that in the case without noise, we don't have this kind of nice result. The results here. We cannot give you the closed form expression on how many time slots are needed to estimate the channels. The main issue is that, yeah, as I mentioned, you have linear equations, and then you need to prove, for example, this matrix is full rank. Then you can say I can uniquely estimate beta based on these linear equations. For fully connected BD-RIS, we have a good way to design phi because this FT is controlled by phi. We can design phi such that we can guarantee this is a full rank matrix. But for group connected RIS, BD-RIS, FT is quite complicated. We do Until now, we do not have a good result. We do not have the answer to control phi such that this FT is a full rank matrix. We don't have this result. So eventually we submit a letter. We submit a letter because we just saw the case with noise. We saw we can use this approach to reduce the trend estimation MSE if you give me a very short pilot sequence. But we cannot analytically characterize the channel estimates overhead in terms of uh, MKU or the number of groups. If you can do this, you can publish a paper. Until now, we are not able to do this. We just submit a letter for the case with noise. We propose some algorithm. We don't have the closed form characterization on how many time slots are needed. Yeah.
Yeah, thank you, Liang. And I also had a question myself.
Yeah.
So the intuition is to exploit the first block Q1 after you estimate it, and then estimate just the parameters beta, right? So the intuition is telling me that if you estimate if Q1 is very noisy, then you will propagate somehow this error. So are there any strategies could we start from Q2, for example?
Yeah, this is a good question.
Or yeah, are
Yeah,
there any
if
strategies
you
to
don't have
decide where?
noise, you can select arbitrary reference
Mm,
M, right? You can use Q1, you can use Q2. In the noiseless case, it's the same. But
mm,
if you have noise, definitely you should select the best reference Q. Maybe Q2 is better, Q3 is better, or whatever. Similarly, I can also say for my first work, this work, uh, when we after we submit paper and many people still ask me, for example, in this work, I also select the first user as the reference user, and others ask whether we can select other users. For example, if the other users has much stronger channel are here, maybe it's better to estimate this. Yes, the answer is yes, but we don't have a very good way. But later, after this work, I found some people, they some published some paper in TWC or TSP, I don't know. They just design an algorithm to select the best user as the reference user, right?
I
And
see.
here it's the same. I think you can say I designed one algorithm to see uh, based on some criterion. I know which is the best reference, right? Not necessarily Q1, maybe Q2, as you mentioned, Q3. But how to select that? Maybe you need to give some criteria. You need to show in simulation your criterion gives very good reference selection algorithm, right? Then the performance is good. That can be something. For the diagonal risk case, I have seen some paper to discuss about how to select the reference channel. Yeah. For BD-RIS, I believe uh, we can still do this. Yeah.
Yeah, thank you. Yeah, I think it's interesting to yeah
Yeah.
to explore also this. Um, Maybe Yang is also asking about the SNR in the simulation. Maybe he's referring to one of the last slides where you had the
What
performance numerical results. Um, what was the value of the
Oh,
SNR?
I don't remember too much SNR. Maybe you can look at the paper. I think you can look at this paper. We have shown the SNR, but now I don't remember. But no matter what's the SNR, the key is that, for example, when k is equal to 3, u is equal to 4, n is 8, m is 16, actually you can use this formula to see how many time slots are required by our scheme. And if you still remember, if I don't do this, right, the overhead is m squared. You can calculate that overhead. Maybe using our approach, we can just use 100 pa parallel signals to do transmission. But if we don't do this, maybe 1,000. So that's why in this regime, right, when the number of parallel signals is around 100, our approach already works. Right? We already have sufficient observations, even if we have noise. But for the other benchmark scheme, because you need 1,000 parallel signals, even if there's no noise, right? If there's noise, then if I give you 100 or 200 parallel signals, then it's not feasible to estimate trend. That's why you can see the MSE is close to 1. It means that the trend estimation error can be very large. But for our scheme, it worked quite well. Yeah.
Okay. Okay, Liang. Thank you so much for the talk, for the interesting
Yeah.
Q&A session. Uh, any other questions? If not, this will conclude our talk. Let us thank again the speaker, Liang. Thank you so much.
Okay. Thank you.
And that's it. So see you if you want in 2 weeks for the next webinar of the series.
Yeah. Yeah,
Bye
yeah.
bye, everybody.
Okay. Bye bye.
Bye, Liang.